So in this lesson, we're going to look at homologous series on the first slide, and then we're going to go into aromatic compounds for most of the slide, most of these slides. And at the very end, we're going to do organic halides, another family. But we can do organic halides really fast because there's no new rules. Instead of writing methyls, you're just going to write chloro if there's a chlorine coming off, or fluoro if there's a fluorine, or ido if there's iodine, or bromo if there's bromine. So that's really simple, and that's what we'll end with. The concept of homologous series is really important to labs and experiments and manipulated variables. If you want to do an organic chemistry experiment, often you'll make a homologous series your manipulated variable. Okay? A homologous series is a series of molecules within the same family, but it's more restricted than that. Okay? All the members of the series have to just vary by one extra carbon. And when you add in that extra carbon, 2 hydrogen go with it. Everything else has to stay the same. If you have a double bond 3 carbons over, you have to keep that double bond 3 carbons over and just keep growing the other end. If you have a branch, if it's a 3-methyl, you have to stay 3-methyl as it gets bigger and bigger and bigger. So everything stays the same, we just make it one longer. Okay? And hopefully that makes sense. That would make a good manipulated variable. Maybe you want to see what is the effect of having a chlorine 2 carbons from the end as the series gets longer and longer. Okay? So you keep making everything a controlled variable except for the length. That's your only manipulated variable. Okay? So we're going to look at the homologous series starting with propene. Okay? So I'm going to draw this just to give us a better understanding. Prop, 3 carbons, ene, double bond, no number, so it's telling us there's only one option, and it actually doesn't matter where I put it. I could have put it on the other side and it would still be propene. It'd just be the rotation of what I drew. But it's a prop 1-ene with the number dropped. The next member of this homologous series has to leave the double bond in the very first position and just grow by 1 carbon. So we're going to go from 3 carbons to 4 carbons. I have to keep the double bond in the very first position. Okay. Now this isn't a proper drawing, but I'm just going to put these little dashes in. I find all those H's clutter the diagram. Okay. But realize you can't do this on a test or quiz or exam. Students do this a ton when they're just practicing. If you have an exam and it's multiple choice, how many isomers are there? Students will draw like this all the time because it's just answering how many isomers are there. I'm not grading you on that. Is everybody okay with what I've done here without putting the H's in? Okay. So now we've got to name this. With the propene, I didn't need a number. But once I add another carbon, I have to include that number because the double bond could have been in the first or the second position. And now I have to say it's in the first. So that's a but 1-ene. Okay. And without drawing, who could tell me, somebody who hasn't answered today, what the next member would be? I feel like you answered today. You've definitely answered. Has Valentina answered a question today? I'm not sure you can. What would it be? So I just missed the first part. Yeah. Perfect. Doing the names of these is super easy. All you do in a homologous series is expand the stem by 1. Everything else would stay the same. Now you may have to add a number in. So prop to but to pent to hex to hept, you just keep expanding it. I do, thank you. So again, I'm going to stop drawing. The next would be, so quite easy to do. You really don't need, I started drawing them just for the sake of teaching, but you really don't need to if you understand it. Okay. So then this last one can go fairly quickly if we pick up that same pattern. Methyl butane, I'm going to draw that and then I'll stop drawing. Butane, 4 carbons, meth with no number. So I have to figure where it would go. Well, it can't go in the 1 position because that would be a pentane. It could go off the 2nd carbon. It could go off the 3rd carbon, but it really would be a 2 again. So the missing number is 2-methyl butane. Okay. And then I'm not going to draw in all my H's. Okay. So once I kind of see the patterns, I can do another few members of the homologous series really easily. 2-methyl, and I'm going to increase that stem one to pent. I put the number in because in my head, I'm like, once you go to pent, the methyl could be in the 2 position or the middle, which would be the 3 position. So I need that number again. Okay. And then the next member, 2-methyl hexane. Okay. Now, any molecule following this pattern is still a member of the homologous series. So I could skip a whole bunch of consecutive members. 2-methyl decane is also a member of the same homologous series. Okay? It's just not the consecutive one. You could do an experiment where you do every 2nd member of the homologous series. They're still members. Sometimes students think if you don't write them out in exact order, they're not members, and that's not true. Anything following that same pattern is a member of that homologous series. Okay? Now you're not going to do any design labs for me, but you go off to post-secondary, just a concept of manipulating controlled variables. I'm controlling the methyl. I'm manipulating this. Maybe a pharmaceutical company, they kind of know a certain formula has the right biological effect, but they want to run an experiment, maybe manipulate one thing, manipulate that chain length and see, okay, if there's a little longer, shorter chain, have a better biological effect or a worse one. Okay. So we're going to leave homologous series. Before I do, is there any questions on your ability to answer a homologous series question before we do aromatics? Okay. So sort of a big jump, different concept, aromatic hydrocarbon. Okay. Everything we've done so far is called aliphatic. Okay, and I'm going to come to that word and it's going to be written out on this slide. So anes, enes, ines, anything without these rings is an aliphatic hydrocarbon. Okay, everything we've done so far. Okay. If you have an aromatic ring anywhere in the structure, we call it aromatic. So what is one of these rings? Okay. So anything aromatic contains a benzene ring. What's in the benzene ring? The first piece of evidence we're going to use to deduce this ring structure is the fact that it's nonpolar. There's no positive or negative end to this ring. Okay. So there's a whole bunch of polar bonds, but they all cancel each other out. Second piece of information that chemists have learned is its molecular formula. Weird, we haven't seen a formula like this yet. C6H6, and it's a liquid under SATP. So it's not a 2N plus 2 or minus 2. It doesn't fit anything like that so far. Okay. And we know all the bond lengths are the same. Okay. There is not a double bond. And this will be addressed a lot in this slide. Again, everything we've done before that doesn't have one of these rings is called aliphatic. Ane, ene, ine, cycloane, cycloene. I'm going to draw one way that chemists draw benzene. So it's a 6-membered ring. Is that too far or is that okay? So 6 carbons. I'm going to connect them in a ring because we know it's in a ring. There's 6 hydrogen. A logical correct deduction is each carbon has an H. Is that okay? Not all. So I'm not quite done. I've got all the pieces out, but I don't have bonding capacity isn't being followed. If we look at this carbon, it's got 1, 2, 3 bonds. It's missing one. The only way to kind of make this work based on your Chem 20 skills would be if you stick a double here. This carbon now has 4 bonds. That carbon now has 4 bonds. This one doesn't, but I can double up again, and I get 4 bonds, 4 bonds. These 2 aren't correct, and I can do that. And based on Chem 20, that works. In Chem 20, you'd mark that right. And we draw benzene like this. You will write this down as benzene. You will see it on tests. Unfortunately, it's not a good picture. You'll use it. And one reason it's not true is you could easily have drawn this slightly differently. And this would be another acceptable way. I just as easily could have put the double bond the other way. So I started at the top, I went to the left, I could have gone to the right. How does a benzene decide which way to put the double bond? Well, it doesn't decide. The truth, what does benzene look like? Does it look like this? No. Does it look like that? No. You can draw either of these. The truth, what does benzene look like? It's the average of both. And we have no notation to draw the average of both. But in your head, on a test, what does the bonds actually look like? The answer is the average. Okay? So let's figure out what the average looks like. Okay? You can draw that, but the truth, we're going to focus in right there. What is the average of a double and a single? Yeah, 1.5. Okay. What's really there is a bond that's 1.5. If you looked at the energy or the length of the bond, it matches a 1.5 bonds. Okay. If you think of there being 3 bonds in total, 1, 2, 3, and you divide it by 2 structures, 3 bonds averaged out over 2 structures, it averages out to a 1.5 bonds. And that's what we see all the way around benzene. All of these bonds are really 1.5. But we don't have any, there's no notation. There's no 1.5 bond. We got singles, we got doubles, we got triples, but sorry, science isn't that simple. Chemistry isn't that simple as our cookie cutter Chem 20 models. It's more complicated than that. So our models, we draw like this, but there's no actual double bonds there. It just fits bonding capacity. All of these bonds are the same length, 1.5, 1.5, 1.5, 1.5, and that matches the observation that all bond lengths are the same at 1.5 strength, 1.5 length. So this is a totally flat ring and there's no positive or negative end to it. And it's really stable. It's much more stable than if you took the total energy of a double and a single, the energy sits a little lower. Okay, and in physics and science, lower energy is more stable. Okay, this is higher potential energy. It's less stable. That is lower potential energy. It's more stable. It's kind of in chemistry, it's weird to think of more, less energy, more stable. But in physics, it makes total sense. Less kinetic energy is more stable. Less potential energy is more stable. Okay, lower energy total in the bonds is more stable. So that's our benzene ring. So this is if you're doing a full structural diagram. That is rarely used, and it is used. I'm not going to use it very much. The diploma doesn't use that drawing a lot. It'll use it a little bit to make sure every one of you can deal with it. What's used a lot more often is the line structure, which looks like cyclohexane. And then to denote this bond and a half, all these electrons are really, they're called delocalized. If you look at the extra electrons are free to go around and around the ring, delocalized, not in one place, and they average out to 1.5 bonds. Okay. How many electrons are in a bond? 2. Okay. Chemical bond from last year is 2 electrons. So if we have a bond and a half, and there's 2 electrons in each bond, there's 3 electrons between each carbon. Okay. But this electron is free to go around the ring. If one electron goes here, one from down there takes its place. So that's what I mean by delocalized. But there's an average 3 electrons between any 2 carbons. Okay. The line structure, to illustrate that delocal nature, that uniqueness of a benzene ring, just puts a circle. Okay. Gets rid of that alternating double bond that's a lie and not true to begin with. So that's one of the nicer ways to do to illustrate a benzene ring, and this is the line version. Okay. Now I just want to highlight a few things that are not benzene. Okay. I want to use line structures. Okay. That is not benzene. Okay. That's cyclopentene, just one double bond. Okay. That is also not benzene. We have a name diene, but that's cyclopent 1,3-diene. It just has 2 double bonds. It's got to have 3 double bonds. Okay. If I do that, another line structure, that is benzene. If I go every second one is a double. It conveys a lie that there's a double bond, but it is acceptable to use because we don't have a 1.5 bond notation. So you can use that, you can use that, you can use those. These are just not benzene. Now, I joke about this, and then I get results. And you kind of get teased if you get this wrong. How many double bonds are in benzene? 0. There are no double bonds. They're all bond and a half. On the diploma or test, when you're asked how many double bonds are there, the only acceptable answer in benzene is 0. There are no double bonds. When we do reaction chemistry and we learn about addition reaction to double bonds, benzene doesn't react like as other addition chemicals that do addition chemistry because there is no double bond in it. Even though we draw it like that, there's no double bonds. Okay. Okay. And that's why that line structure is probably the best illustration we have. Yes, this is just, benzene's very unique, and all of this just applies to benzene. Okay. If you have this structure, that has 2 double bonds because that's not benzene. It's not one of these unique rings. When you put a third double bond here, these electrons delocalize and average out around the ring. These aren't delocalized. Those electrons are right there. Okay. So now we're going to do the typical naming rules when you have one of these rings. Naming aromatic compounds, and we'll start with one benzene ring, one side group. We're going to name the alkyl group. We know how to do that. Okay. And then for the stem, we're not going to count. We're not going to add an ending. We're just going to use the word benzene. Okay. There's no need for a number because there's only one alkyl group. It's in the one position. So I've just pre-circled the benzene ring. Now students have to look carefully. Okay? Your diploma loves to really make sure you understand what a benzene ring is. You've got to look. You see double bonds. You've got to make sure there's one, there's two, there's three. So yes, that's benzene. If there's not three, it's not benzene. Okay? And it turns into the lie that there's actually no double bonds in that ring. Okay? Sure. More? Yeah. And then I put a side group off the benzene ring. Okay. It doesn't matter where it is. This side group could be up here, and it's still the same structure. Okay. That is 2 carbons. So the alkyl group is ethyl. The core of the molecule is this unique ring, ethylbenzene. So next we're going to move into what if there's 2 alkyl groups that are the same, and then we'll do 2 alkyl groups that are different, and then there's one more last twist before we end aromatics. Does anybody need me to wait? Everyone's good? So benzene ring of 2 alkyl groups. Really, there's nothing new here. You've dealt with 2 alkyl groups before. Name the alkyl groups. Determine positions by minimizing the numbers. You've been doing that already. You're just practicing your workbook. Add benzene at the end. So we do have a benzene ring here. So that takes care of our stem and ending. We're just using benzene. I have a CH3 that's not connected to the other CH3. They're separate. Okay? They're coming off different parts of the ring. So I have two separate methyls. Anytime they're next to each other, they're going to be a 1, 2. No matter which one I start at, neighbors are 1, 2. If I start here, 1, 2. 1, comma 2. Dimethylbenzene. Now you'll find that there's only 3 possibilities if you have 2 alkyl groups that are the same. I just want to show you the next 2. I don't want to have you bother writing these down. So just watch it. It's a bit redundant, but I do want to show them to you. Okay. My second example is an example of the 1, 3. 1, 3 has obviously a 2 position, a gap of 1 in between the 2 groups. And the furthest they can be is when they're at the 2 opposite ends. Now 1, 2, 3, 4. And if I number the other way, it would still be 1, 4. Okay? So those are your only options when there's 2 identical groups. 1, 1, 2, 1, 3, 1, 4. You should never have 2 of the same numbers because you can't put 2 branches off the same corner of a benzene ring. Okay? So really not new, same as you would if this was cyclo anything. It just happens to be benzene ring. Last, and you've been doing this already, what if there's 2 ways to number? You're going to go alphabetic just like you've done in the past. So I'm going to put in a benzene ring. I'll do this version. You've seen that alternating triple bond on a lot of slides. That is something else you'd have to recognize as benzene. So I put a methyl on the top, and to the right, I'm putting an ethyl. There's what we're going to treat as our stem. And I've got to decide, well, I've got a ethyl there. I've got a methyl there. It's a 1, 2, but how do I decide where to start? And I'm going to do it alphabetic. So this is an ethyl. This is a methyl. So I'm going to go with the E first. So this is going to be my 1 position because it came first alphabetic. This will be my 2 position. Okay. If you had 3 alkyl groups, you would start by whatever one comes first alphabetic, but you wouldn't do all 3 alphabetic. So the first letter is your 1, and then you'd minimize the numbers. Okay. So don't put them all in alphabetic, just get the first one. So this is 1 ethyl, 2 methyl, benzene. I definitely need the numbers because this could have been 1 ethyl, 3 methyl. Okay? I need the numbers to know where they're located. Okay. So similar to before. Last, all of these compounds are aromatic, and there's one other example of where you'll see a compound that's aromatic. You can have this benzene ring that's not the center of the molecule. It can just be a side group. And annoyingly, when it's a side group, we give it a different name. So you have to be familiar with a different name if this ring isn't the center, is just a branch itself. And that's this last slide. When a benzene ring is added to a compound as an alkyl group, we call it phenol. Okay? And this would be a C6H5. Okay? The 6H is lost because it's been added to a ring. The second sentence is most important. As an alkyl group or as a branch off something, benzene is called phenol. You're seeing that same YL that's been through all the branches. And I threw this into a great big long name. It looks super confusing, but you just decoded one piece at a time. I want to give everyone a chance to get that name down before I start decoding it and dealing with that phenol wording. Okay. So when you get a great big long word, we're used in the English language, you want to start there and go that way, but that's not how we deal with names or decoding them. You start with the stem. That's our starting point. Then you deal with the family at the end. And then you're going to go way to the start and work your way back through all the alkyl pieces. So that's the sequence. Following these steps, it's not that complicated. It's just a whole bunch of simple steps. Pent. 1, 2, 3, 4, 5. 1 ene. First carbon-carbon connection is a double. Now we're going to jump to the front. 2-methyl. Okay, so I'm going to stick my star in. I've been numbering. I put this in the 1 position, counting from that side, so I can't change that. The left is my 1 position. I could have done everything from this side, and I just do the mirror image, but I've picked that side. 2-methyl. 1, 2 is a methyl. 3,3-diphenyl. Okay. So we're seeing this phenol word for the first time, and that's just an aromatic ring, but it's coming off something. So there's my 3rd carbon. I have to come off, and then I have an aromatic ring, and I'm going to use the line structure. It's the simplest to write. That's one of the 3s. There's another phenol in the 3 position. I'm going to go up. Okay. If I don't put the circle in the middle, I'm wrong. If you forget to put it, that's a cyclohexane. Okay. That now makes it phenol. Okay. This whole molecule is now aromatic. Okay. Because it has 1 or more benzene ring, we call this aromatic. There's my 2 phenols. I did that. I'm done. One, 2, 3, 4. That one's good. So it started with a really complicated name, but if you go piece by piece, it's not too bad. Let's end this section with the line structure of this guy. I haven't done line structures in a little bit. Again, start with your stem. Go back to step 1. Pent. 1, 2, 3, 4, 5. Lift. There's my stem. And the first carbon-carbon bond is a double. I've got a branch, a methyl. That's 1 carbon. Okay. When you do your branches, drop your pen and say 0, because that carbon's already counted for. So I'm going to drop on the 2, 0, 1, lift. That's a methyl. Okay. Again, I said 0 because I'm on a carbon that I already counted, so I don't want to count that again. 3,3-diphenyl. There's my first carbon, my second carbon, my third carbon. Okay. Doesn't really matter what angles you go. I've got the most room going down. So that's where I'm going to put my phenols. If you put them up, that's fine. This molecule isn't really flat, so we're squishing it anyway. We're not showing the proper bond angles. We're not showing a 3D projection. Okay? And that's all my pieces. We don't write in H's. So that's the line structure. And that ends all the C's and H part only of this course. We're finally going to get a little more exciting. We're going to do something other than, who would think you could spend 2 whole days on just 2 atoms? But they're 2 fairly important atoms. So let's throw some oxygen in the mix. Actually, sorry, halogens. Oxygen, I don't think I'll get to till tomorrow with our alcohols. Okay. So last slide of the day, because you know pretty much all of these patterns that we need to do organic halides. Okay. Yet another family. Okay. It's the first time in my notes I've used the word derivative. A hydrocarbon is CNH only. A hydrocarbon derivative has some other atom added in. Okay. We're doing organic halides, so it's a halogen, but a derivative could be any other atom, O, S, N. So we have at least one hydrogen replaced with a halogen. And you probably don't even need me to teach you, and you could probably decode that name without me. I'm going to go through it, but hopefully you could logically decode it. So we're not going to use the full name. We're going to use fluoro, chloro, bromo, and ido. Just the first few letters of each of the name. Okay. So there's the chloro. So same as usual, start with the stem, then go to the end, and then you come back to the front. So bute, 1, 2, 3, 4, all single bonds, nothing else to add in. I need to pick a side. Donna, what side would you like me to pick? It doesn't start on the right or start on the left? The left. Okay. Okay. Another student could start on the right, and it's correct. When I give you a quiz and I mark it, I can't write one answer on my piece of paper. Somebody could start on the left, somebody could start on the right. Almost nobody will do it, but you could have fun and go top to bottom if you wanted in your board. Okay. We don't tend to do this because it's a bad use of paper. I tend to go right to left, but you can. So Donna said start on the left, so that's my 1, 2, 2 dichloro. So I've got 2 chlorines, both in the 2 position. 1, 2, Cl, Cl. Every other bond on the carbon would be a hydrogen. This is a full structural formula. I haven't condensed anything. Every bond is showing. I'll do the line structure. We've got a shift now. We have something other than C and H. Okay? You have to explicitly write in any atom that isn't a C or an H to a line structure because it's the only way you'd know. Yeah, it would still be saturated, yeah. We don't deal with the aromatics. The saturated terms don't apply because you got this bond and a half. It just, the Alberta Ed answer is it does not apply. Okay? But this is saturated. But don't worry about aromatics. So line structure, I got to do stem of 4, 1, 2, 3, 4, lift, second carbon, first, second, has 2 chlorines coming off of it. I do a dash. Okay? If I don't write anything there, there's a carbon. But if I write a symbol, I'm replacing the carbon at the end with whatever atom I just wrote in. And I have to put a second one. Now there's no methyl groups. There's chlorines at the end. So that's the correct line structure for 2,2-dichlorobutane. Similar to what we've done before, sometimes you drop numbers. Trichlorofluoromethane. There's no numbers there because we got meth, 1 carbon. Okay, we don't need numbers. We don't need to say 1, 1, 1 trichloro. There's only one option. 1, 1, 1 trichloro, 1 fluoromethane. None of those numbers are needed. Okay? And where you put them doesn't matter also. Okay? They're all going to be in the one position. So chloro, 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 fluoro, or any rotation of that. Okay? If I do the line structure, and this one's going to be a bit of an oxymoron to get started. What is the line structure for methane? And again, it's an oxymoron. It would be a dot. The line structure for methane is a dot. Nobody's done. I joked with past years, if you want to bug your English teacher and they put a period, ask them, is that a period or is that the line structure for methane? They won't laugh or chuckle. They won't know what you're talking about, but I'll get a kick out of it. So that's the line structure for methane, but then I have to put the side groups, chloro, 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 fluoro. So line structures with methane kind of look a little weird. I'll end with this. And ask you to name that and write it down. So I'll be quiet for maybe 45 seconds, a minute. Hopefully you can get the name out. And then I'm going to pick someone. I'm not going to ask for a volunteer. Did Ethan get a name out yet? Yes or no? Let's write that down, Steve. Chloro. Does anybody agree? Looks right to me. So this is where my strategy would be to circle the end of line segments. I'm not going to circle this one because there's a Cl there, so there's no carbon there. So we've got 2 carbons, ethane. We've got a chloro coming off, but no matter whether it was here or there, it'd be at the end or the 1 position. So he correctly did not say the number. You don't need it. Okay? Chloroethane, good answer, good job. And that's our organic halides. Okay? Now I didn't do any examples, but you could mix you could have a methyl and a chloro or a fluoro coming off the same molecule, and you just apply the same rules that you've been going through. You know how to name a methyl, you know how to name a chloro, you can put them into the same name.